Welcome everyone for this distinguished webinar series in AI and cybersecurity. It is my distinct pleasure to invite Dr. Prabuddha Chakraborty from University of Maine. Dr. Chakraborty's research interest lies in intersecting areas of artificial intelligence, Internet of Things, and system security. He received his PhD in electrical and computer engineering from University of Florida. He has worked within security software team at Texas Instruments and the FPGA acceleration R&D team at Xilinx. His research effort has so far led to more than 20 peer-reviewed journal and conference articles and more than 10 US patents and copyrights filed and granted. He is a recipient of the Certificate of Outstanding Merit from University of Florida in 2021 for his academic and research excellence. He's also received several awards and honors for his research contribution, including the TTTC's E.J. McCluskey Best Doctoral Thesis Award 2022, Best Hardware Demo Award at IEEE Host 2019, and Top Picks in Hardware and Embedded Security Award in 2021 by IEEE HSTTC. Dr. Prabuddha, it is my distinct pleasure and invites you for this webinar. And we are so grateful for you spending your time and effort today. And the floor is yours.
Hey, thank you. Thanks, Prakash. Thank you so much for the wonderful and very nice introduction. So I'll just share my slide and get started. So as Prakash mentioned, I'm Prabuddha and I'm with the University of Maine. And today we will look at how we can leverage artificial intelligence or AI towards establishing a robust hardware root of trust for edge devices. Okay, so let's get started. Today's presentation will be divided into a few sections. First, we'll look at IoT, understand what IoT is, what are its applications, and what are the challenges that are being faced by IoT and its applications. And from there, we will look at how we can secure the edge hardware through different learning techniques. First, we'll look at two works that I've done, SAIL and SURF, which will try to quantify the security of a hardware lock design. I'll explain more in details later. We'll also look at a work called Lego, which will try to iteratively harden a lock design through different learning techniques. And we'll also look at different AI techniques for exploring the hardware Trojan space and detecting hardware Trojans in hardware and digital design. And after that, we'll summarize and we'll conclude. What is Internet of Things and what is edge? I'm sure you all know what IoT is, but let me still go over it. IoT consists of embedded systems, which are sensing different values from the environment or different processes, and actuators that are doing certain things to the environment that is directly interfacing with the outside world. So these are called edge devices. There's a lot of connectivity involved. These edge systems, these embedded devices are all connected in different ways between each other. They're connected to the cloud. And then there's a good amount of smartness that are being also integrated into these edge devices or into the cloud infrastructure for doing different processing, for feature extraction, decision making, and so on. And finally, we also need to incorporate security in these embedded systems and in this cloud server to ensure that the application is doing what it is designed to do. So when you have all these things, you have an IoT system. That's a complete IoT system. And traditionally, computation was done mostly at the centralized server, or as we call it, cloud, right? And this paradigm of computing was called the edge intelligence paradigm. And slowly we are moving towards a new paradigm. We are trying to do most of the computation at the edge itself because we want to reduce the load on the cloud servers, because we have so many devices that are connected, 20 billion in 2019 devices that were connected. It's not possible for the cloud to serve all different queries and data processing. So the edge has to do some of these things. So we are moving more and more towards this edge intelligence paradigm. And this IoT is being converted into what we're calling it AIoT, or artificial intelligence of things. Now, when all these AIoT and IoT systems are being used, pretty much everywhere, they're in home automation, industrial automation, automotive, agricultural applications, retail, environmental monitoring, medical application, and so on. Specific examples could be something like a set of drones that are trying to detect forest fire. And we have connected autonomous robotic systems that are doing industrial smart manufacturing. We can also have connected vehicles. That's a very good example of IoT system, like vehicles that are smart, that are talking to each other, that are automatically navigating the different terrains, right? And IoT is indeed transforming our lives. It is a huge market. It is expected to be 1.8 trillion by 2028 with a 25% growth rate. And many of these applications that we see here are relying a lot on edge intelligence and edge processing, right? So that brings us to the question, what are the challenges that are being faced by current IoT and AIoT system, especially in light of recent trend of doing the computation in the edge system? So first is the data storage and processing aspect. We're storing a huge volume of data. The variety of data is also very broad. We have images, we have video, sensor data, etc. And even within each category, the image domains or the sound domains or the sensor domains vary quite a bit. For example, if you have maritime surveillance, the images are very different than forest fire, right? And the velocity of data is very high as well. So that's one problem. Communication is a big problem too, because we had 50 billion devices that were connected in 2020, and this an old number is growing every day. And communication has become a huge problem as well. And security is also a very important factor, and it is becoming more and more difficult to secure the systems because we have these edge systems, right? And these are smart edge systems that are doing all this data processing, that are doing all these interesting communications between each other and with the cloud. Now, we have to make sure that these edge systems are trustworthy and they're doing exactly what they need to do. We also need to ensure that these edge systems cannot be stolen, or this intellectual property that we have put into these systems cannot be reverse engineered and stolen, right? So that is important to ensure. And edge systems have both hardware and, of course, the software component, and the security of both is important. And they're, again, connected to the network and connected to the server. So we have to ensure the security of this entire stack. So that's a security challenge. And to top it all, the edge systems are typically resource constrained. They have limited storage space, battery life, communication bandwidth is limited, data velocity is high, they have to serve complex queries and things like that. So that makes things worse, because now not only do we have to come up with solutions for all these problems, you have to also make sure that they are resource efficient, right? So today we'll focus mostly on this edge system security, and we'll try to see how we can create secure edge systems, and we'll try an approach from the hardware perspective, because hardware is very important for these systems, because these edge systems tend to be very simple, right? They have a very simple architecture in terms of the hardware, and they have a very bare bones software running on it, right? So, and the software cannot be too complicated because of all these resource constraints. So the security sort of has to come from the hardware side as well, and potentially it will be cheaper than securing the system from the software aspect. Okay. Now, all these edge systems have to be first manufactured. The hardware component has to be manufactured. And modern hardware systems have a lot of small different intellectual property components in them. They have drivers, IPs. IPs are intellectual properties. For example, if you are designing a modern system, you may have a security module, you may have a compute module like CPU, you may have a multimedia module, you may have a GPU module, you may have a connectivity module, a display module, a camera module, and so on, sensors, etc. And it is very difficult for a single entity, especially for a small and medium scale industry companies, to design this entire system from scratch, right? So what they tend to do is that they buy these individual components from third-party vendors, we call them third-party vendors, and then they integrate into their system. And then from there, they build the rest of the system, and then they fabricate it, and then they use it in their edge device, right? Now, a lot of threats that can originate from this entire manufacturing process. So let us look at how it's done. So you have the third-party IP vendors, or 3PIP, and they provide the third-party IPs to the IP integrator or the design house, and the design house sort of puts all this different intellectual property together, write their own component as well, and they synthesize it, do some optimization, creates the physical layout of this entire system, and then they send it out for fabrication. and we get the final product. Now, all these components or all these steps may not be done at a single facility. Sometimes these steps are done at a very different locations. For example, the third-party vendors are definitely different than someone who's doing the IP integration. There could be multiple third-party vendors that are selling different IPs, right? And the IP integrator generally integrates the system, and then they may give it to some other company to do the synthesis and optimization and creating the physical layer. And from there, the design can go to a different fabrication facility, and sometimes that is outside, say, US or outside a specific country or different country, and then it gets fabricated there, and the final product is sent back to the design house for final integration and selling, pretty much. So a lot of components are there, a lot of entities are being involved, and we need to ensure that we can trust all these entities. And it's really hard to trust all these entities in certain scenarios. And due to that, we cannot be sure if whatever designs we are getting from, say, the third-party vendors or whatever product that has been manufactured by the fabrication facility can be trustworthy. And that leads us to some of these attacks that is possible at these different stages of this supply chain. There could be malicious modification that have been done to the design either by the third-party vendor. The third-party vendor can sell you a bad or a malicious design, and it's really hard for you to detect it. And you just put it in your design, it comes back fabricated, and now it's vulnerable. Your entire system is vulnerable, right? So we call this the malicious modification or hardware Trojans. And this hardware Trojan can also be inserted in the fabrication facility as well, because you're giving your design to the fabrication facility. They can put some extra logic gates in there. And we have shown that even if you add one gate, you can create a hardware Trojan with just one transistor. So now if you think about billions of transistors in a system, the fabrication facility has added only one transistor in there. And it's really hard to detect that one transistor out of all those billions of transistors that are out there in modern systems, right? So it's a difficult problem to solve. There could be threats in terms of reverse engineering and IP theft, intellectual property theft. And this is a very big problem. For example, you design something and you give it to the fabrication facility, and the fabrication facility pretty much just sees whatever you have designed. I mean, they have access to your design, so it's really easy for them to figure out what you have done. And then from that point, they can make some minor changes and then resell your entire system for a cheaper price through a different market. So that's the intellectual property theft. So they're stealing something that you have developed over 5 years, 2 years, 3 years time. And there's also unauthorized use. You have designed something that should be only used by a specific entity, and it's really hard to kind of lock a hardware. And we'll see some ways to do it. And it's a hard problem to do. The idea is that, can I lock a hardware? Can I build, say, a processor which does not work until I provide a certain key value or I provide a certain secret? You can get access to the processor, but you will not be able to run it or use it. So that's unauthorized use, and we have to prevent such unauthorized use, right? So security is an important parameter, especially for edge systems, and essentially it's important to ensure security during the design phase itself. We need to understand what security threats are possible for specific edge hardware and need to secure that, and need to be aware of that from the design phase itself. And it's the foundation of creating a secure and trustworthy IoT and cyber-physical system. Because if your hardware is not secure, there are Trojans in there. There's someone stealing your hardware. They're making changes to your hardware. They are masquerading as you. So they can steal your hardware and they sell it in your name, and that will ruin your image. So if you have all these issues going on in your hardware level, it's really hard to build an entire system on top of this untrustworthy hardware, right? It's a difficult problem to deal with. So we need to build these systems to be secure first. So first work we'll look at is called SAIL, SURF, and LEGO. It's a trio of work. And what we'll try to see how we can secure this edge hardware through a technical logic locking. And we'll essentially see if we can lock the design and prevent unauthorized access and also prevent reverse engineering, okay? So we want to lock the design both from a functional and structural side. So let's look at it. So what is logic locking? A logic locking is very simple, actually. So you have your original design, which you can think of as just a few gates connected as a graph. And then what logic locking does is it inserts some extra gates into your design and then connect it to some key inputs. We call them key inputs. These are actually primary inputs that we create. Essentially, what it means is that you cannot operate your design without providing the right value of the key. Okay? So it's like encryption in a way. It's an encryption of a hardware. So your design is not locked until you provide the right key. Your outputs will not be correct. Your outputs will get corrupted, essentially, if you provide the wrong key. So this will ensure functional security and will potentially prevent unauthorized access. And then what we do on top of that is we resynthesize the design and we introduce some structural changes into this design. So it looks very different than the original design. And because of that, we are also introducing a structural obfuscation kind of approach where it's really hard for someone to look at the design and figure out what the design is supposed to do. In other words, it's really hard for someone to do a reverse engineering kind of attack. So this step ensures structural obfuscation, prevents reverse engineering. So with this logic locking, we can eliminate two of the problems that we have in the supply chain issue, especially for edge hardware. First one is unauthorized access. Second one is preventing reverse engineering and IP theft, intellectual property theft, right? Typically, the strength of logic locking has to be measured in two different ways. Functional formulation. So you take the lock design. Once you do your locking, you take the lock design. You come up with a functional formulation. You give it to some solvers, and you essentially attempt to retrieve the key. And if the solvers fail to attempt to retrieve the key, then you can say, okay, my design is secure to some extent, especially from a functional aspect. I cannot really solve for the key. So there are different techniques like SAT, FSAT, SMT-based techniques that have been proposed that try to make sure that the design that you're creating is actually secure from a functional perspective. No one can, kind of put it to a SAT solver and get the key out. So that was great. This set of works have ensured the functional security of lock design. But when I started working on this particular project, and that was back in 2018, we saw that functional security has been adequately addressed, but the structural aspect was not. The structural changes that were being introduced were not good enough, and that we believed could lead to reverse engineering, and that could also open a pathway for a future functional attack as well. So now let's explore that avenue. So to be sure what we are thinking, what we did was we ran some small tests, and what we observed was the structural changes that are being introduced due to logic locking and the synthesis thing that people have been doing, synthesizing the design after locking. The structural changes were actually very local. The diversity was very limited. So that is, only a few types of transformations were happening before and after synthesis. And essentially, there was a heavy bias in terms of the kind of changes that were happening and the kind of structural changes that are being introduced. So that led us to believe, okay, if there's so much bias here and the diversity is so limited, can we, come up with a learning algorithm to reverse this effect of structural change that was being introduced? And that's exactly what we did. We came up with a training set, and I'll come back to the training set, how we created the training set. That's very interesting. But essentially, we created a training set consisting of pre-synthesis and post-synthesis design snapshots, or essentially you can think of them as designs. And we trained an AI model to reverse this effect of synthesis, thereby reversing this effect of structural obfuscation that was introduced. And once you have this AI model trained, you just provide a design and evaluation, and this model can unlock the design structurally and also quantify the structural difference of the design. A little bit more about the training data set, because that was very interesting. What we did there was, what happens is when you do the locking, you have this original design, and this is from the defender's perspective. The original design gets locked. So the defender adds a few extra key gates and locking gates into the design in, say, in those blue regions, right? And then we do a synthesis, and the synthesis step was supposed to introduce changes in those areas, right? Structural changes in those areas. So let's say it did do some structural changes in those areas. So that is represented by this red. So these blue areas are now changed to these red areas, right? And then the attacker gets hold of this design only after it is synthesized and locked, right? This is the assumption that the attacker do not have access to anything else before that stage. because that's the point where we provide the design to other entities outside the specific cell. And the attacker gets hold of the design. What the attacker will do is attacker will insert more locking gates using the same algorithm that was used for locking. And here we can definitely assume that the algorithm used for locking is open access, because that's the fundamentals of encryption, is that your algorithm cannot be secret. So attacker encrypts the design again using the same algorithm, and these are the regions. The green regions are where the attacker has then put in different logic gates, locking gates. And then the attacker will do one more resynthesis on this design, and these green regions would then transform into yellow regions. And now, from this point, the attacker knows, because the attacker has done the locking this time, the attacker knows exactly how the transformations are taking place for this design and for this specific locking algorithm. So the attacker will now use these green regions and this yellow regions. So the yellow regions would be the post-synthesis regions, and the green regions would be the pre-synthesis regions. So the attacker now can create a map between what was there and what it became after synthesis. And the attacker did it completely on the same design it was asked to attack. And then with that information, the attacker will attack the original synthesized lock design on the top right. So from that, we were able to create the training data set directly from the design that we're trying to evaluate. So we call this technique pseudo self-referencing, because we are referencing the same design. It's not perfect. That's why we're calling it pseudo, because we are locking, or we are getting the data set from already locked design, not from the actual original design. But it was good enough. So we could create the data set from the lock design and then unlock the same design. So we were using the same design to help us. We're using the lock design to help us unlock it, in other words. This made our attack completely oracle-less. So we did not need anyone we did not need any extra information other than the lock design. And we did not need any golden design or a unlocked design to do this attack. So it was extremely powerful at that time, because all the other evaluation techniques required oracle. So essentially, a lot of results here, but what we saw was that we could pretty much structurally unlock most of the standard logic locking techniques out there with very good accuracy. And one might say that, 60 to 80% accuracy is low, but it's not, because we are trying to predict the entire design, what it was before synthesis, right? So we are predicting a graph. We are not predicting the key or 0 and 1. So the space of the prediction space is quite large, because we are predicting a graph. So 60 to 80% one-to-one match or accuracy is actually quite high considering the situation. And we also defined different metrics to understand how much recovery we are doing. And we also saw that we were very resilient to predicting bigger graphs, bigger subgraphs, and so on. So that was great. So we could kind of reverse the effect of synthesis, and we wanted to take it one step further and say, okay, can we now do a functional attack? Can we, now that we have reversed the synthesis process, can we now predict the value of the key itself? And if we can do that, now we would actually unlock the design from a functional perspective as well. So what we did was we looked at these exposed localities that were generated from cell analysis. And then we came up with another algorithm called the SERF, which was refining this, which would predict the key value from looking at the cell recovered graph, the logic locking key. It would predict it, and then it would refine it with some optimization techniques. So using this approach, we were able to get 100% of the key back in many cases, 40, 80%, and so on. So we were able to retrieve most of the keys completely in many cases, and thereby functionally unlocking the design as well, not just reversing the structural obfuscation. We could now also do functional attacks. So it was a complete flow now. And we had pretty much good success, more than 90% accuracy in terms of key recovery, and a box plot over there showing that we could unlock many designs with 100% accuracy. And one might say, okay, well, you just retrieved 90% of the key. You still did not retrieve 100% of the keys, right? Your encryption if you do not have 10% of the key correct, your encryption may still work, right? You may not be able to still unencrypt it with just 90% of the key, but that's not true for digital design. And how logic locking works is, if I can guess 90% of the key correct, and we did some experiments, quantitative experiments, we saw that we could get the input output of the design to almost match in up to 80% of the times. So the IO, or the input output, was matched 80% of the time. So your design is 80% functionally unlocked. For 80% of the input that is being provided, the output is correct. For 20%, it may be wrong. And in some cases, 100% was correct. So there you go. And we also saw that only a few output pins were getting corrupted output because those keys we could not get correctly. So there is a lot of usefulness in partially unlocking the design, because there are a lot of approximate designs, approximate circuits like FIR filter and image filters, and nowadays we have AI techniques. If I can get 80–90% of the time the outputs to be correct, or image processing techniques, right? If I can get 90% of the time the output to be correct, the small amount of noise that is being introduced may not be significant enough depending on the application that you have. So there is a lot of benefit in partially unlocking the design as well. So what we are driving at here is, we did all these nice attacks, right? But the goal was to secure the design. So that was the entire goal. We're not trying to discredit anything here. And essentially, we used these attacks, and we came up with different other metrics to essentially quantify the effectiveness of locking, right? So if you did a locking, you have come up with a technique to lock your design. It's great. What you need to do next is run or use your design and see if SAIL can unlock it, or SURF can unlock it, or other attacks like SAT that was not proposed by us, can they unlock it? And the goal was that can we use these attacks and this matrix to come up with essentially measures of how good the locking was for a given locking technique. And we exactly did that, because once you can quantify the goodness of a logic locking technique, you can then improve it, right? If you know it's bad, then you go back and you make some changes, and then you try again. And now if it's good, then great. So that's a good locking. So to kind of formalize this approach of locking, we next came up with another word called LEGO, which was learning guided logic locking. What we did was we would do an initial locking of the design. We would put some key gates there, and that would lock the design. And then we had this database of matrix and attacks, essentially, like we discussed before. We had SAIL, SURF, SAT, SIVA, and so many other metrics. We would evaluate it. And then we'd figure out, is it a good stopping point? You know, am I happy with the kind of evaluation that I'm getting? Am I happy with the matrix? If I am, then great, then you stop. If I'm not, then I would relock the design, essentially, with using different strategies that we have come up with, and an expert system that we have developed, where you relock the design, and then this flow will continue until we are happy in terms of the locking, in terms of the lock gate that we received. And we ran this on different designs, and these are some of the results. And we saw that within a few iterations, we could pretty much reduce the attack accuracy of many attacks. Here you can see SAT, SWIFT, KSA, and many other attacks. You can see that all these attacks, the accuracies are sort of tapering down, and within 3, 4, 5 iterations, it's all below 10–20%. So we were able to secure a design with the help of the matrix and with help of this iterative logic locking scheme that we have developed. And the good news was that it was converting very fast. It is scalable, that it can incorporate new attacks in the future, because we have this database. The whole framework doesn't have to change. All you have to do is put in a new metric there, or put in your own metric there, or come up with a new attack, and from there you can derive a metric. Just put that in there, and this whole flow will still work. And it is progressive. That is, you can terminate your locking process at any point. You can say that, hey, I'm happy with, you know, some of the attacks having 30% accuracy. I'm okay with that, but I do not have enough time to, you know, run this process for too long. So you can just say, okay, I'll terminate early. That is possible. So you can trade off security for design time. So that is also possible. And that is something new and different, at least was different when we proposed this one, right? So that was all these three works, they kind of chained together, SAIL, SURF, and LEGO. They together provided a proper systematic way to secure edge hardware, or any hardware for that matter, towards ensuring that those hardwares are not vulnerable to reverse engineering, those hardwares are not vulnerable to unauthorized access, those hardwares are not vulnerable to intellectual property theft, essentially. So that was those three works. And we'll switch gear a little bit and let us now look at what we call Trojans, right? Trojans are very buzzword nowadays. So we'll see how we can use AI techniques to first explore the Trojan space, and then next we'll look at how we can use the AI techniques to detect Trojans. First, we need to understand what Trojans are, or what kind of Trojans can be inserted in the design before we even do detection. So that's why we call it exploration. First, we need to understand what a Trojan can do. So what are Trojans? Trojans are essentially malicious modifications, like I mentioned before, in your design. So say you have an original design here, which is, again, a bunch of gates connected as a graph. And one of those entities in the supply chain we saw earlier could insert one of these extra logic in there in your design. So here you can see on the left side, the denial service Trojan. The attacker has inserted 2 extra gates. That's all, 2 extra gates. Essentially, when the trigger conditions are met, the payload will corrupt one output. So corrupt one wire value. So because this one wire value is corrupted, that can lead to a privilege escalation, that can lead to a denial of service, that can lead to a lot of different things. So Trojans are very simple. You just need to add a few gates in the design, and then it's it. That's it, done. And it's really hard to detect it because of that, because you have billions of gates and billions of transistors. How do you detect a Trojan in such a huge space? So malicious modifications and a lot of possibilities, because I can insert this Trojan in so many different ways. I can do it with different gates. I can use more gates. I can use less gates. I can make it more complex. I can make it less complex. I can make it do different things like leak information. The one on the right side, bottom right, that particular Trojan will leak information through different side channel techniques. So a lot of possibilities in terms of Trojans, and the Trojan space is big. So we need an automatic way to explore this Trojan space, and that's the next work we wanted to do, because we need to first understand what's possible here, right? And then we can see, okay, how do you detect that? So question was, can AI help here? And it sure did. So what we ended up doing was we created this sample Trojans as a guiding point for a given design. So we came up with a design, say, hey, this is the design we wanted to analyze. Now let us see what kind of Trojans can be inserted. So we came up with a few sample Trojans. Hey, looks like these are great Trojans in this design, and this can be generated through semi-automatic techniques or through manual effort. So we come up with some sample Trojans. And then from that point, we looked at the sample Trojans and trained 3 different models. We trained a trigger model, a payload model, and a Trojan model. So the trigger models were essentially classifiers that would look at the design, the original design, and would tell us that which particular nets or wires can act as a trigger. So triggers are essentially the wires that can be used to start the Trojan activity, essentially. And the payload is the specific construct that does something. In other words, for the denial of service Trojan, the payload here, you can see on the bottom left, is doing the corruption, and the trigger is triggering the payload, essentially. So we first come up with these 2 models that could, act as a classifier and figure out which nets or which wires can act as trigger and which wires can act as a payload. And then we come up with a generative model, a Gaussian mixture model for designing the Trojan itself, or the entire Trojan body. And here we use a generative model because we wanted to introduce some noise and some level of differentiation between what we have. So we provided a few sample Trojans, right? We do not want to come up with the same sample Trojans. So we wanted to come up with other Trojans. So maybe similar to the sample Trojans, but still different. So that's why we had the generative model. And through these 3 models, we were able to come up with Trojans that were similar to the sample Trojan, but at the same time different. So that was the key. It has to be similar enough, but at the same time, it has to be still different. Right? That was challenging. And what we saw here, this is a huge amount of results. You don't have to understand all this. You can read the paper. But highlighting that specific column, you can see that we were able to accurately generate valid and potent Trojans. Essentially, we were able to, in many cases, with 90% accuracy, in some cases less, we were able to get really good Trojans that were similar to the sample Trojans, but not too similar, not the same Trojans exactly. And here is a visual representation. So the blue dots, I believe, were the Trojans that we trained on, and the reds one were the one that we generated. And this is the feature space distribution. So we can see the Trojans that were being generated had similar features with the Trojans that we trained on, but they're not exactly the same, right? So they are not the same Trojan, but they are similar Trojan. And that's exactly what we wanted to do, and that's exactly what we did. So through that, we were able to come up with huge amount of Trojans, which are potent and which were good. And from that point, we could then, come up with different strategies and see, hey, how can we, defend against some of these Trojans? And that would be the next work. Say, okay, now we have detected this Trojan. How can I defend against some of these Trojans that we have, that we think is possible to be incorporated in this design? Detecting in the design phase, again, this is a Trojan. You put some additional logic in, and that becomes a Trojan. What we do is for detection is we extract features for every wheres and every nets, other word nets. We extract different functional, different structural features like static probability, transition probability. If you're not familiar with this, do not worry. Essentially, we are just trying to extract different features. If you know AI at least, just essentially extracting different features for everywhere in your design. And the goal is that we'll then classify everywhere, whether it's a Trojan ware or not a Trojan ware. Essentially, that's how simple it is actually. But I think the previous step was very important towards even doing this. This approach is we had the data set generated through the automated Trojan exploration scheme, and from there we could actually do this training and come up with a model that can actually detect real Trojans. And so essentially you come up with these features, and you for each where you classify. And at the time, this was 2018 when we came up with this first work, and we were able to come up with different. We essentially construct a voting ensemble of different models, and that would give us a final prediction whether a given where net is actually a Trojan ware or Trojan net. And we generated a lot of training data set from the Trojan exploration scheme, and then we tested, but we did not test it on the same Trojans, because that would not be fair. What we did was we then tested it on standard Trojan benchmarks that are present in TrustHub. TrustHub is essentially a website or essentially a community that has a lot of Trojans and other things like puffs and other things there. You can look at those designs there and do different attacks or come up with your own techniques and post them there. Cat for Assurance is another website that is really great for hardware security. So essentially, we use a standard data set, and we are able to detect Trojans in that standard data set using the model that we trained, this ensemble-based model that we trained. So that was detecting a Trojan at a design phase. So this detection is only possible if you have access to the design or the net list, or if you know exactly how the gates are connected. This kind of detection is possible. But what happens if you don't, right? You are given a particular chip, it's fabricated already, and I say, hey, can you tell me if there's a Trojan in it? Oh, it's a really hard problem to do. So this is post-fabrication, right? There are two ways to do it. First of all, you can reconstruct this graph here from the fabricated chip, and there are ways to do that. They delayer the chip and they put it under a microscope, they reconstruct the chip. It's a really hard work. Or you can try to do some kind of sidechain analysis where you measure the power, you measure the electromagnetic waves, etc., and you figure out whether a Trojan is there or a Trojan has been activated and things like that. So we'll go the second route where we'll see, okay, can we detect Trojan post-fabrication stage through sidechain measurements? And when we started, okay, so what we did was, hey, we had an idea that, hey, if there are additional logic in the design, that would lead to higher power consumption, especially when it's triggered, right? So if you have extra 2 gates or 10 gates in your design, that would draw some extra power. It has to, theoretically. But the problem was, you can see the graphs here. We have the Trojan free, and the one with the power waveform for Trojan and the power waveform for Trojan free. You can see that they look very similar. It's really hard to figure out whether a little bit of power was drawn for 1 gate in your 2 billion gates design, right? It's not an easy task, and even the differences were very similar. So it was really hard for us to manually detect a Trojan just by observing the power waveform. But we still knew that theoretically it should consume more power, and there should be some signal in this waveform that we can use to detect a Trojan activity. And we essentially use AI here too. We kind of clustered. We figured out a way to convert the waveform into a feature. More details in the paper. Essentially, we converted into a different extra different features out of the waveform, and we were able to cluster the different waveforms into multiple clusters. And here you can see that there are different clusters are being formed, and one of the cluster is Trojan free, and the others have different types of. Essentially, it can not only cluster, not only figure out which cluster had no Trojan or which design had no Trojan, it can also figure out which designs had similar Trojans. So that was very interesting too. So, and that makes sense, it should, because the Trojans are different. If the architecture of the Trojans are different, then they will draw different kind of power, right? If you have a very big Trojan, it will have a very different waveform. If you have a very small Trojan, it will have a very different waveform, right? So it makes sense that it was able to distinguish between the Trojans itself as well. So here we have 8 types of Trojans and 1 Trojan flea. We also use different, we also tried using SVM and other decision tree and other classic machine learning algorithms to detect Trojans as well, and that was also successful as well. So both clustering and standard ML-based classification techniques work for this kind of Trojan detection as well. So with that, I will summarize without taking too much time, and I would be happy to answer questions, and I think that would be more interesting. In summary, IoT systems are widely used in industrial automation, transportation, and many other applications pretty much, and in future, everyone will use IoT. There are a lot of threats that are there, that are existent in the semiconductor supply chain, and that in turn can lead to an insecure system, because the edge hardware can get compromised in the semiconductor supply chain during its fabrication. And if you have a malicious chip or a malicious hardware, that will in turn make your edge device malicious. And if your edge device is malicious, it will make your entire IoT system malicious, right? So we have to at least ensure the hardware is trustworthy, because it's really hard to repair a hardware. It may be easier to repair a software. You know, you come up with a patch and you immediately fix billions of software components out there. But once you fabricate a hardware, if it has a problem, it's really hard to debug it. It's really hard to, first of all, detect it, and it's also really hard to fix it. It's almost impossible to fix it in certain cases. So we came up with different AI-guided techniques that could detect malicious modifications in the hardware at the design phase. This is prefabrication phase, like during these techniques can be used by the third-party vendors, IP integrator during synthesis phase. And we also came up with AI-based reverse engineering techniques and unauthorized access prevention technique, logic locking. So we came up with techniques using AI to prevent reverse engineering and prevent the theft of intellectual property during this supply chain, during this fabrication process. And we also came up with AI-based techniques to detect malicious modification post-fabrication through side channel measurements as well. So with that, I'd like to thank everyone, and thank Prakash and thank the organizer for inviting me, and I'm open to answer any questions that you have.
Thank you, Dr. Prabuddha, for a very insightful talk. I hope people can hear me. And if people have any questions, feel free to put that information on the chat, so we can able to relay this question to the speaker, so we can able to have an engaging conversation. While we wait, the first question is from Dr. Tasik Kim. Is there any reason to use AdaBoost algorithm?
That's a good question, Tasik. Essentially, we were observing that some of the Trojans were not being overlooked, and we wanted to see if some kind of a boosting technique would help. And that's why we tried AdaBoost, and it worked for us. It was essentially a quantitative, based on quantitative analysis, we were able to select AdaBoost. The theoretical foundation of that was we had a few examples that were kind of an outlier, and that had to be boosted so that we could, detect them properly. And then we tried AdaBoost. We tried other techniques as well, and AdaBoost gave us the best results. So we went with AdaBoost. Does that answer your question, Tessie?
Yeah, I think okay. Is the next question we have is there any deep learning model could be used for Trojan detection?
Yeah, absolutely. There are a lot of works that have been done since we published our paper in 2018. A lot of work have been done by Kento Hasegawa from Japan, and he has come up with a lot of different models to detect hardware Trojans, different deep learning techniques and different neural network-based techniques. But the fundamentals are still the same. You need to understand we are extracting a certain type of features, and then we are giving it to an AI model, and then it detects it, right? But before we do that, we need to have this exploration. I think that is much more interesting, this exploration phase. How do I come up with the data set to even train my model? I can come up with cool models every day, but how do I create this data set? That is also very interesting. But yes, to answer your question in one sentence, yes, there have been deep learning models have been proposed that can detect hardware Trojans, yes.
I have a question. How do you see, because it's primarily, these are looking at very hardware level, chip levels, when we look at very massive IoT environment, how do we look at those logic lock states, in a much more, situational awareness perspective, when you look at a big, network point of view? I think you're looking at, at an individual hardware, but how do we scale this type of techniques, what we do, and to detect these Trojan-based attacks?
Well, there have been, of course, some interest in Trojans that can that can exist across different hardware innate systems. I think that there have been one paper on synchronous Trojans. What happens is that they trigger all the Trojans at the same time across different hardware. Especially this was shown for power grid, that they could turn off different critical infrastructure, and they did it at the same time, because you have to do it at the same time. Otherwise, if it is localized, then someone can detect and potentially prevent such an attack. So they had to come up with a way to synchronize the attack. So there have been work in the hardware Trojan domain that does look at the big picture, and that tries to have coordination and things like that. Yes.
And I think I'm going back to the question. So I see, how do you evaluate sale attack resilience of a lock design, and and how one should look at mitigation approaches? And not sure that's yeah. So in general, how do we how do you see resilience for this particular area, for to measure the resilience metrics for evaluating Trojans? Do you think there's a need for more resilience metrics as we look at intrusion of all these Trojan-based attacks? And most of our attendees are actually students, postdocs, and computer science, electrical engineering. So I'm going to follow up with that in a bit broader way to see, how do you see, as an expert on this area, for challenges for how should students look at Trojan-related research in the futuristic thing? What is your advice?
Yeah, I mean, I think the question also talked about SAIL. So yeah, SAIL attack resilience. What you do is you pretty much run SAIL, and SAIL, the accuracy of SAIL, or the structural recovery accuracy of SAIL, and different metrics that we have developed in SAIL can help you figure out how good your locking was in terms of structural defense. So that would be that's exactly how you use SAIL as a metric. And then in terms of defense, you essentially have to introduce changes that are have to go back a lot. So let's see. So essentially, you have to introduce changes that have a lot of diversity. So this line, this curve on the lower left corner, this has to be flat, right? If this is flat, then we have all types of rules are being used to carry out the transformation. So there has to be some level of randomness in terms of the kind of structure changes that are being introduced. The rules that are being used has to be uniformly applied, and that would definitely defend against attacks like, say, 100%. And Prakash, like you said, in terms of future, I definitely think that the structural security of digital design is very important. It has been largely ignored till 2018, 2019. Now there are a lot of works that are coming up in terms of defending the structural integrity of digital design. And but it's still a new area, and I believe that a lot of more work can be done in terms of defending reverse engineering of digital hardware and preventing IP theft through different structural locking and innovation techniques there. In terms of hardware Trojan, it's a hard problem because we have so many possibilities in terms of what hardware Trojan means, right? You can insert one gate, extra gate, and that is a hardware Trojan, or you can insert a very complex thing, and that's a hardware Trojan too. So we need to come up with better ways to capture the Trojan space, and we came up with one way using AI techniques, and by no means that's the only way to do it. And I'm sure that there are other ways and other innovative techniques that can be applied to first figure out what kind of modifications are possible and viable. I think that's the first step in terms of defending against Trojans. I mean, once you know that, then you can come up with a model to detect it, right? But first you need to know what is possible. So that would be my advice from the hardware Trojan aspect. One other thing I'd like to say is that these embedded systems, the hardware software co-security aspect is very important. One need to understand, I know there are a lot of students from CS, like you mentioned, and I understand they may not be interested in the hardware aspect, but a lot of different attacks are possible. I did not present it in this particular talk, but I have also worked on timing search analysis. Timing search and attacks works where you need to understand the interaction between the both software and the hardware to be able to detect those timing search and vulnerabilities. And I believe AI can also play an important role. I did not apply AI for that specific work. That's why I did not present it here, because this was an AI venue. But I'm sure AI can be applied in terms of detecting timing search channel, in terms of fixing timing search and vulnerabilities with both software and hardware knowledge together combined. And that's where CS people can definitely work and look into and collaborate with the ECE people, to do that and make that happen.
We have one more question. Does chaotic security circuits have any scope in AI-based structural security?
Yeah, I think that is a very good question. I definitely think that more work needs to be done in terms of seeing if chaotic theories can be applied. And I believe that, yes, I think it may be able to either defend against AI-based techniques in terms of when the AI is used for attack. I'm sure that the whole idea of defending against AI is that you need to make things random enough so that the AI cannot pick up a signature, right? If the AI cannot pick up a signature, it's not going to work. So that should be the goal here, is to kind of make the life of the AI model difficult. And yes, I definitely think that I'm not an expert in chaotic theory or chaotic security, so I cannot really comment with great authority here, but I definitely think that's a great area of research.
While we wait for one more question, but I wanted to just remind readers that there is also Dr. Prabuddha is also the editor for a new journal for we are looking for papers for on supply chain side attacks. Can I share that screen? So maybe
yes,
people can.
Absolutely.
This may be a good way to. I'm not sure where is that. Oh, do you have that? Do you have that in your screen article? I can't find the link.
I can pull it up one second.
Journal. So while we wait for a couple of questions to see if we can do it, it may be a good way to promote this as we have more people here. And so it's a Springer journal. We're looking for a journal for it's looking at any papers related to side channel attacks at FPGA level, at ASIC level. Trustworthy microelectronics is the topic. So it's due sometime in April, I believe, and we'll post that information on our website too. So I encourage anybody is interested to, or working in the area or wanting to contribute, please. Look into that.
So, do you see the screen?
Yes, thank you.
So this is the special issue. It's called Trustworthy Microelectronics. It's in the Journal of Hardware and System Security in Springer. So feel free to contribute here. These are the topics, topic of interest, and the deadline is April 10th, 2023.
Great. Super.
So yeah.
Thank
so if
you.
take notes if you want to. It's pretty much everything to do with system security. We are very broad, and definitely will also consider software level security, hardware level security, hardware core security is of very interest to us. Supply chain security, side channel, dynamic side channel, power side channel, those kind of things, architectural level innovations to secure systems, absolutely, all those things. And emerging areas too, if you have papers related to smart grid security, security of AI hardware or AI models in general, yeah, feel free to send.
Great. Thank you, Dr. Prabuddha. I don't think we have any more questions, so I think we'll wrap up here, and appreciate your time and effort. As a token of your time today, we will be sending a nice flag and certificate signed by our dean and our directors for this Center for AI and Cyber. And appreciate so much for your time, and we will make this recording available online so people can still, for those who had a chance to watch it. And thank you again for your time. We'll continue to seek and working with you as more opportunities come.
Yeah. Thanks, Prakash. Thanks, Niru. Thanks, Jameson. Thanks, everyone. Thank you.
Thank you.